50 degrees, the vertical is a little bit longer than the horizontal. That looks good. So this is the V0y. This one is the Vx. This is the actual. And we know this is 10, and that's 50. Okay? So same construct applies. Vx is equal to V0 cosine theta. Vx is equal to 10 cosine 50 Vx. Um, 6.43. Okay. And the y. Sine 50. So it should be close to 6.43, but a little bit bigger. And survey says 7.66. That makes good sense. So 10, 6.5, a little more than 7.5. I feel good about that. So far, so good. So now that we have the construct down, let's read the question. It says, does the ball land on the ramp or the plateau? All right, and when it lands, what are the magnitude and angle of its displacement? Well, that's actually a really tough question, and there's a couple different ways to do this. So let me show you the couple different ways to do this, and you can tell me what you think. So the first one we're going to do is we're going to say, if the ball is launched, okay, if the ball is launched, when it gets to a height of 3.6 meters, what is the delta x? So the ball is going to go up and then come back down. So when it gets to a height of 3.6 meters, what's the delta x? That's the real question. Okay. So let's do the horizontal and vertical and answer that question. So let me write it on the board so you know. Okay. First question is, what is the delta x when delta y is equal to 3.6? So that's the first question. Okay. So let's do the horizontal and vertical pieces to this real fast. Okay. This is delta x, dx, t. This is delta y, v0y, dy, a, and t. So we want this to be plus 3.6. This, we know from here, is 7.66. We don't know what this is. We know this is negative 10. And we're going to need the time, because we're going to do the time, then we're going to plug it in here. Okay? So delta y is equal to 1/2 gt squared plus v0yt. Positive 3.6 is equal to negative 5 t squared plus 7.66 t. So I'm going to subtract 3.6 from both sides. Okay? And when I put this into a quadratic solver, it turns out there's no time in which that's the case. It says it's imaginary, which I was a little confused by, but what that means is that given this, the ball actually never gets up to a height of 3.6 meters. Which seems to me to be a little weird, like, how does it never get that high? Okay, let's verify that result. Okay, I'm going to find a quadratic equation solver. Okay, so my A value is -5. My B value is 7.66. And my C value is -3.6. And I don't know if you can see this or not. Let's check. Ooh. Okay. Assuming I did that, it says it has complex roots, which means that there's no time. There's no time that the height is 3.6, which means it never gets that high. Well, if it never gets that high, then I think we've answered the question. Right? We've answered the question, does it land on the ramp or the plateau? But there's another way we can answer this question. So let's hold on to this answer for a second. Okay? So let's hold on to this answer for a second. And let's ask a different question. The different question we can ask is, what is the delta y when the delta x is 6? So this time, we're going to assume that it's going to get to 6 meters, but we want to know what the height is. If it gets to 6 meters and the height is bigger than 3.6, that should be a good indication for us. And so what we're going to do here is we're going to say, okay, so this time my delta x is equal to 6. My v in the x direction is 6.43. All right, so delta x is equal to vxt. So 6 is equal to 6.43 times t, so that time is equal to 0.93 seconds. So delta y, -5, this is 0.93 squared plus, what's my v0, 7.66. And I solve for delta y, and it turns out delta y is 2.8 meters. Which means that the path of the projectile is more like this, right? When it gets to the 6 meters, it's below that. So given the first two questions I asked, I think it's pretty clear that it does not end up on the plateau. It's got to end up somewhere on the ramp. So how do I even figure out that? Because it wants to know now, if it hits somewhere on the ramp, so it goes on a path like this, if it hits somewhere on the ramp, what are the horizontal and vertical components? Now, we know the horizontal component, but let's get to the vertical here in a second. Okay. So, in order to do this, we're still going to need our horizontal and vertical component stuff here, okay? But we got to get a little tricky. So if I come over and I look at this problem here, what is this angle right here? We're going to call this angle, this Greek letter here, that Greek letter is phi, okay? That Greek letter is phi, and how do I represent phi? So here's the opposite side, here's the adjacent side. So what I notice is the tangent of my angle phi is equal to, basically it's d2 divided by d1. So the tangent of my angle phi, so that's 3.6 divided by 6.0, okay? So that's an idea. I want to keep that in mind. And no matter where it lands, okay, right? No matter where it lands on this ramp right here, let's say it lands right here. That's the height it lands. That's the horizontal distance. Because this angle theta is here, we know the angle is the same, so the ratio should be the same. So this, in this case, tangent theta is also going to be equal to, well, this is the change in the vertical, and this is the change in the horizontal position. So this is delta y divided by delta x. So we now have a relationship between how far it goes horizontally, how far it goes vertically, and the angle, which we can get the angle from this statement right here. Oop, I did it again. Fine. So, if I were to use my horizontal and verticals again, right, I'm going to come up here. All right, so we know that's true, we know this is true, we know this is true, we don't know the time, but I can relate those two things right there. So, you can do this one of two ways. It's not that big of a deal. Do we solve for theta? Is that what we do here? Okay. So, given this construct right here, I'm going to say that my delta x, let's do a delta y. We can leave delta x so we have this here. So let's write our equation down here. Delta y is equal to 1/2 gt squared plus v0 yt. Delta y is equal to delta x tan phi negative 5 t squared plus 7.66 t. Okay? I like that equation. Let's do this one over here. Delta x is equal to vxt now, I have this equation with two unknowns. I have this equation with two unknowns because I actually know tan phi. If I look over here, the tan phi is just equal to 3.6 over 6. So I'm going to take delta x and I'm going to substitute it in here. So I have 6.43 t. That's delta x times 3.6 over 6 is equal to negative 5t squared plus 7.66 t. Everybody has a t, which is nice. So I can divide a t out of everybody. This t, one of these t's, and this t. I end up with 6.43 times 3.6 over 6 is equal to negative 5t plus 7.66. Okay, t is equal to 0.76 seconds. Okay, so t is equal to 0.76 seconds. It takes that much time to get to there, which is cool. And what is the question asking? This is 45. When the ball lands with the magnitude and angle of its displacement from the launch point. Oh, okay. So if we have the time, we can figure out what the delta x is, and if we figure out the delta x is, we can figure out the delta y is. Let's work through it real fast. So delta x is going to be equal to 6.43 times 0.76, 4.89. Okay. And that's less than 6, which is good. plus 2.93, which is less than 3.6, so that's good. And so to get the magnitude of this, which is the pink that they're asking for, so to get the pink, 4.89, 2.93. This is the displacement vector. We're going to call it R vector. So R vector squared is equal to 2.93 squared plus 4.89 squared. So the magnitude of R is equal to 5.7. And then, what's funny is the angle is already right here. Like whether we use delta y over delta x or 3.6 over 3. So theta is equal to the inverse, well, it's actually phi, sorry. Inverse tangent of these two. So 2.93 divided by 4.89. So phi is equal to 31 degrees. Okay, that is a complicated problem. I am under the impression there's actually an easier way to do it. I just couldn't come up with it. Okay. Okay, 141. I got a couple more minutes left. Let's keep going. Problem 47. It says batter hits a pitched ball when the center of the ball is 1.22 meters above the ground. The ball is about an angle of 45 degrees with the ground. With that launch speed, the ball should have had a horizontal range returning to the launch level of 107 meters. Okay. So what they're saying here is like, here's the ground. And the ball initially is hit here, 1.22 meters at a 45-degree angle, so it goes. Now, it says to return to its launch, it would have gone 107. That's what it's saying, okay? But what it wants to know is, does the ball clear a 7.32 meter high fence that is 97.5 meters horizontally? So 10 meters back from here, there's a fence. And it's, what did it say? 9 point what? 7.32 meters high. That's the height of the fence. So wants to know, does it clear the fence? If it doesn't, where does it hit it? And if it does, by how much does it clear it? So let's start with the initial construct so we can work backward and get the initial horizontal and vertical velocities of the ball. So I'm sure you're getting tired of this, but it is the way to do these problems. I know that delta x, Vx, t This is 107, okay? So what's cool about this is you know that because it starts at this height and returns to its launch height, the delta y is 0. This is -10. All right? And so when I look at my equations, like delta y is equal to 1/2 gt squared plus v0yt, and this is delta x is equal to vxt. So I have my two equations. The thing that I know is that this ball is launched at a 45-degree angle. So if I look at that, okay, I'll bring it down here. So it's launched at a 45-degree angle. So this is the V0. What's that telling me about the Vx and the V0y then? So if your angle is 45, then this one is V0 cosine 45, and this one is V0 sine 45. So if I plug this in here, this is 0, this is -5 t squared plus V0 sine 45t. So I can solve for t here. So I'm going to add this term to both sides, divide through by a t. So t is equal to V0 sine 45 all divided by 5. This one, I have 107 is equal to V0 cosine 45t. So in this case, t is equal to 107 divided by V0 cosine 45. Now what I like about this problem is sine 45 and cosine 45 happen to be the same thing, so it makes the algebra a little bit easier. But I'm going to take these two t's and set them equal to each other. So I have 107 divided by V0 cosine 45 is equal to V0 sine 45 divided by 5. So I can solve for V0, okay, and 32.7 meters per second. So that is the launch speed. So that's right here, 32.7 meters per second. So what we're going to do now is we know the horizontal distance to this. We know the vertical distance, so we're going to ask the question, what is the vertical displacement when the horizontal displacement is equal to something? 97.5. So basically what we have to do here is we have to do a whole another vertical and horizontal. So